Hello, and welcome to the lecture on 1.12. Today we're going to talk about modeling variation. Let's start with direct variation. Direct variation occurs when one quantity is a constant multiple of another. So what that will look like in an equation is this. If the quantities x and y are related by an equation, y equals kx, for some constant k not equal to 0, we say that y varies directly with x or y is directly proportional to x. K is called the constant of proportionality. A quick example of this would be something along the lines of y equals 3x. Now here, the constant of proportionality is 3, and y is directly proportional to x, namely that y is 3 times whatever x is. Let's do another example here, one where we have to set up an equation. Fennec Shand shoots Din Djarin with her sniper rifle. Din Djarin feels the shot hit his armor before hearing it fired. The distance between Din and Fennec varies directly with the time interval t between feeling the shot and hearing the shot. A, if the constant of proportionality is 327, write an equation for the variation. Part B, if Din Djarin hears the rifle shot 3 seconds after he feels the laser bolt hit his armor, how far is Fennec?
Can I at least have that blaster? Get down! Commando!
So how we solve this problem is first we need to set up the equation, which will be in the form y equals kx, and in this case we're going to use t instead of x because of the time interval between him feeling the shot and hearing the shot. So ours will be more along the lines of the distance between them is equal to k times t. So we'll use this equation instead. It doesn't really matter which variables you use, as long as you have it in the form of one variable is equal to k times another variable where k is a constant. Now, in part A, we already know that the constant of proportionality is 327. So we know what k is. So our model is just going to be d is equal to 327t. Again, where t stands for the time interval between when he feels the shot and when he hears the shot. And d is the distance between Fennec and Din. And that's it for part A. We set up the equation. Now let's do B. Now we know how long it takes for him to hear the shot after he feels it. 3 seconds. Din hears the rifle shot 3 seconds after he feels it. So t in this case is equal to 3. So if we use this model, we would get d is equal to 327 times 3. And that turns out to be 981. The distance between Fennec and Din in meters is d. T is the time interval between feeling the shot and hearing it. This is just so that you have a better understanding of the question. If you go back through the question with these definitions, it might give you a better understanding. All right, I want you to try one now. The amount of money the Separatists spent, S, on the Clone Wars is directly proportional to the amount the Republic spent, R. If the Separatists spent 450,000 at the same time that the Republic spent 300,000, write the equation of variation. Suppose that the Separatists spent 6 billion. How much did the Republic spend? Okay, so how you want to approach this problem is start with the equation given here, S equals KR. You need to find K. Now you already have a relationship between S and R in terms of these numbers. So figure out what K is in part A and write the equation. And then in part B, you'll use that equation to actually figure out how much the Republic spent at the same time that the separatists spent $6 billion. The next thing that I want to talk about is going to be inverse variation. If the quantities x and y are related by the equation y equals k over x for some constant k not equal to 0, then we say that y is inversely proportional to x, or y varies inversely with x. The constant k is called the constant of proportionality. Let's do a basic example first, and then we'll jump into another one. So if we have something that looks like this, y equals 12 over x. This means that y varies inversely with x. So as x increases, y is getting closer and closer to 0. As x gets closer to 0, y increases without bound. And graphically, it would look something like this. Here's x, and here's y. So as y gets really large, as x gets really large, you can see that the y value is really small. If x is really close to 0, then y gets very, very large. Let's do an example here. Cloud City mines Tabana gas on Bespin. When Tabana gas is compressed at a constant temperature, the pressure P of the gas is inversely proportional to the volume. If the sample of Tabana gas occupies 1.2 meters cubed and has a pressure of 75 kilopascals, find the constant of proportionality, then find the equation. If the same sample is compressed to 0.6 meters cubed, find the new pressure. This problem is very similar to your try one problem. So here, we have an inverse relationship between pressure and volume. Specifically that the pressure is inversely proportional to the volume. So we would end up with something like this, where P, for pressure, is equal to K over V. So this is our model so far. We need to figure out what K is, where P, of course, is pressure, and V is volume of Tabana gas, both. Okay, so we need to figure out what K is. In part A, it says that the gas occupies 1.2 meters cubed and has a pressure of 75 kilopascals. 1.2 meters cubed is a volume, 75 kilopascals is a pressure. So we say 75 is equal to K divided by 1.2, and we just need to solve for K in this case. So if we multiply both sides by 1.2, we actually can solve for K very easily. And we see that K is equal to 90. So our model in part A is P is equal to 90 divided by V. Now we have our model for this particular problem. We just need to figure out what happens to the pressure when the sample is compressed to 0.6 meters cubed instead of its 1.2 meters cubed. So now for part B, what we do, part B, we use this model, P equals 90 over V, when V is now equal to 0.6. So we do P is equal to 90 divided by 0.6, and 90 divided by 0.6 is 150. So P is equal to 150 kilopascals. All right, the next thing that I want to talk about is when we mix these variations. Now let's do a definition here. If the quantities x, y, and z are related by the equation z equals k times xy, where k is a non-zero constant, then we say that z is proportional to the product of x and y. We can also say that z varies jointly with x and y. Now this is very much the same definition as direct proportionality. If we just think of x, y as a single term, then you have z is equal to k times that. If the quantities x, y, and z are related by the equation z equals k times x divided by y, then we say that z is proportional to x and inversely proportional to y. We can also say that z varies directly with x and inversely with y. And this should make sense with our previous definitions. If you ignore y, then z varies directly with x. If you ignore x, then z varies inversely with y. So we can say direct variation and inverse variation with the respective variables. Let's do an example of this because most equations actually don't have a direct or inverse variation alone. Most pairs of variables anyway. Most of the time we actually have multiple variation. This example is Newton's law of gravity. So if we have the force of gravity is equal to g, which is a constant. G is the gravitational constant, times m1 times m2 divided by r squared, where m1 and m2 are masses of the two objects, and r is the distance between those two objects. We could say that f is directly proportional to m1 and m2, or we could say that f varies jointly with m1 and m2, and inversely proportional to r squared. And again, we are always inversely proportional whenever we have a constant divided by something. Even if there's something else in the numerator, that just means that we have multiple variation instead of a single inverse variation or a single direct variation. So in this case, f has a direct variation with the product of m1 and m2. We can also say that f varies jointly with m1 and m2. That's going to be it for today. I will see you all in the next lecture.